Welcome back. We left off last time with the question, where did this wacky, ginormous number even come from in the first place? How did we get 6.022 times 10 to the 23rd as the number of things in a mole? Well, the answer to that comes from a guy named Amedeo Avogadro. He was the person to discover, in a sense, this number, or to at least maybe a better way of putting it would be to realize the significance of this number. What he realized is that if you have that number of an atom or a molecule, so if you have 6.022 times 10 to the 23rd, for example, copper or carbon atoms, the mass of that sample in grams will be the same as the atomic mass from the table. So if you remember, carbon, for example, has an atomic mass of 12.01 AMU. So the average carbon atom weighs 12.01 AMU. If you have this number of carbon atoms, then you will have that same number of grams of carbon. So what this allows us to do, and this is actually really significant, even though it might not seem that way at the beginning, this concept of a mole having a certain number of particles equal this value of a mole. What this allows us to do is to relate the mass of something to the number of particles that we have, which is actually really significant. Because when we're doing chemistry, what we care about is the number of particles that we have. We don't care about the mass of something. If we were, for example, reacting carbon with oxygen to form CO2. So we had some kind of reaction like this happening to form CO2. Remember, oxygen is a diatomic element, so it would be O2. We're not going to take 1 kilogram of carbon and 1 kilogram of oxygen and make 2 kilograms of CO2. It's not going to work like that, because carbon atoms and oxygen atoms have different sizes. The oxygen atoms, just even one of them even, is larger than carbon. And so because they have different sizes, we can't take equal masses and get them to react together to form this new molecule. Some of them will react, for sure, but it won't react completely. Instead, what we could do is we could say we could take 1 mole of carbon and 1 mole of O2, and that would give us 1 mole of CO2. Because moles are talking about the numbers of particles, not their masses. And so it's really the number of particles that we're interested in when we're trying to figure out how much of this one thing do we need to react with something else. Because the molecules and the atoms are interacting with each other, they're not interacting with a mass of something. So it's actually really important, even though it might not seem that way at first, it's actually really important that we can relate the mass of something, which is how we measure material. We don't really have a way of directly measuring the number of atoms in a sample. That's just too difficult to do. Instead, we measure the mass of something, and then we can use the molar masses from the periodic table and Avogadro's number to figure out how many atoms we have of the material in that sample. So this is actually really, really important. And this is why we use this seemingly random and ginormous number. Is because if we have that number of things, then we will have the same mass in grams as the atomic mass from the periodic table. And really, honestly, from this point forward, I'm not even going to refer to the atomic masses on the periodic table as atomic masses. They are, and they still are, but we will more often use them as what we call molar masses, which is the number of grams per mole. So from this point forward, with maybe only a few exceptions, those mass values on the periodic table I will refer to as a molar mass, the number of grams that 1 mole of a material weighs. Okay. So this is kind of talking about the same thing that we're just talking about there. So we can calculate the molar mass from the periodic table just like we did with the formula masses in the last chapter at the end there. So if we were to look, for example, at gold, so gold, if we look at the periodic table, has an atomic mass of 196.97. So that is the average mass in AMU of 1 atom of gold, but that is also the number of grams per mole for gold. So 196 point, did I say 97, is that right? Yeah, 196.97 grams per mole. Again, we are just taking the number from the periodic table, and whatever that mass number is on the periodic table, that is the number of grams in every mole of that material. So sulfur is going to be 32.06 grams per mole. And lithium is going to be 7, what is it? Well, roughly 7, 6.97, or sorry, 6.94 grams per mole. So each of these samples here, each of those masses of different materials have the exact same number of particles in them, which seems wrong at first because you think, how is that possible? Because again, we have way more mass with the gold here than we have with the lithium. Lithium, we only have 7 grams, and here we have practically 200 grams. How can we have the same number of things? Well, again, it gets back to this idea that just because you have the same number of things does not mean that the things themselves are the same. So you can have a dozen nails here, and you can have a dozen nails here, but these nails are much larger than those. So these larger nails, even though we have the exact same number as the smaller ones, these are going to weigh a lot more. Maybe 2 or more times more than the small nails do. In the same way, having 1 mole of sulfur weighs about 32 grams, but 1 mole of carbon is 12 grams. We have the same number of atoms in both of these samples here, the exact same number. But because the sulfur atoms themselves are physically larger, the sample is bigger. You can think of it the same way as, let's say you wanted to have samples of different things. Let's say, for example, you had a sample of 10 bowling balls and a sample of 10 marbles. Now you're going to have 10 of each of those, but obviously the 10 bowling balls are going to weigh a whole lot more than the 10 marbles. Unless you just really like oversized marbles or something. And even then, I bet they would still not weigh more than the bowling balls. It's the same thing that we're seeing back here. We have the same number of gold atoms here as we have lithium atoms here, but the gold atoms are like bowling balls compared to the lithium atoms that are like marbles. The gold atoms themselves are just much larger than the lithium atoms, and so when you have the same number of each, the gold is going to weigh a lot more. Okay. And so this is kind of bringing the idea back here to the donuts that we talked about at the beginning of this chapter. So in the same way, if you have a dozen cream-filled donuts, those are going to have more calories than a dozen glazed donut holes. You can still have a dozen of each, but because there's so much more stuff here, it's just a larger sample, these are going to have more calories per dozen than these will. Alright, so let's look at, let's see. Yeah, I think we'll do these real quick, because I don't think those... Yeah, so we'll do these two, and then we will call it for this video, and then in the next video we'll look at some more examples. So let's do these two real quick. So this says, calculate the number of moles of sulfur in 57.8 grams of sulfur. So we'll do this one, I think we'll do it here. So what we're doing here is just a conversion. We're going to take 57.8 grams of sulfur, and we're going to convert that to moles. So if we look at the molar mass of sulfur, that is 32.06 grams for every 1 mole. So the grams here are going to cancel out, and that is going to leave us with 1.80 moles of sulfur. Not quite 2. So again, all we did here was convert from grams to moles, and we did that using the molar mass from the periodic table. So we just found sulfur on the periodic table, found the mass number, that is the number of grams per mole, and we flipped that whichever way we needed to get the units to cancel out correctly. Okay, so this last one here, I would like you to try on your own before I work it out. So this asks you to calculate the number of grams of sulfur in 2.78 moles of sulfur. So go ahead and give that a try. So pause the video now. Okay, I hope you gave that a try. This one, just like the previous one, is pretty straightforward. All we're doing is using the molar mass to convert, but now we're doing it from moles to grams instead of the other way around. So we're going to have 1 mole on the bottom, 32.06 grams on the top. So we're going to cancel the moles out. That is going to leave us with 32.06 times 2.78. That is 89.1 grams of sulfur. Okay, we'll call it there for this video. I will see you all in the next one. We will look more closely into converting between grams and moles, but also converting between atoms and moles, combining the two together. So check that out next time.